Good evening, ma'am. My name is Swati Yadav from 5.8 and my roll number is 5417. My presentation topic is embedding lemma. Now, contents, definition, theorem, lemma used, proof, application, reference, and external links. Now, what is embedding? Let xt and yu be the topological space, then x is said to be embedded into y by E if and only if E is a homomorphism between x and some space of y. That is, to embed a space x into a space y should mean that we can identify x with a subspace of y where identification is up to a homomorphism. Then the statement of embedding lemma. The statement of embedding lemma is let fi from x to yi be a family of continuous functions which distinguishes points and also distinguishes points from closed sets. Then the corresponding evaluation map is an embedding of x into the product space of yi. To prove this result, we need to prove some lemmas. Now, the lemma first is the evaluation functions of a family of functions is 1 to 1 if and only if that family distinguishes points. First, we need to prove 1 to 1. Then proof, let fi from x to yi be a function and let e of x from the product of yi be the evaluation function. Let x and y be distinct points of x. Then e of x not equal to e of y if and only if there exists j belongs to I such that e of x of j not equal to e of y of j. But e of x of j is equals to fj of x by the definition of E. Similarly, ey of j is equals to fj of y, so that the condition e of x not equal to e of y is equivalent to saying that there exists j belongs to I which may depend upon both x and y such that fj of x not equal to fj of y since x and y are arbitrary. Thus, the evaluation function of a family of functions is 1 to 1 if and only if that family distinguishes points. Then the second lemma. The statement of second lemma is let fi from x to yi be a family of functions which distinguishes points from closed sets in X. Then the corresponding evaluation function E from x belongs to product of yi is open when regarded as a function from x onto e of x. Proof, let V be an open subset of X. We have to show that E of V is an open subset of E of X. A typical point of E of V is of the form E of X for some X belongs to V. Now, X belongs to V is a closed subset of X not containing X. So, by the hypothesis, there exists J belongs to I such that Fj of x does not belongs to Fjx minus V. Let G is equals to Yj minus Fj of x minus Y. Then G is an open subset of Yj and so product of J inverse G is an open subset of product of Yj. We claim that product of J inverse G intersection E of X belongs to E of V. For suppose Y belongs to product of J inverse G intersection E of X, then Y is equals to E of Z. For some Z belongs to X, product of J in of Y belongs to G, and so product of J E of Z belongs to G, where Fz belongs to G, since product of J of E is equals to Fj. From this it follows that Zv, since otherwise Fj belongs to Fjx minus V, contained in Fjx minus V is equals to Yj minus G. Thus, Y is equals to E of Z belongs to E of V, as was to be shown. Now the set product J inverse G intersection E of X is open in the relative topology on E of X, and clearly it contains E of X, showing that E of V is a neighborhood of E of X in E of X. But E of X was a typical point of E of V. Then E of V is a neighborhood of each of its point in the relative topology on E of X. So E of V is an open subset of E of X. Since this holds for all open sets V in X, we see that E regarded as a function from X onto E of X is open. Then remark, the converse of this lemma is false. Let x is equals to r square and f1 f2 be the two projection on r. Then the evaluation functions is simply the identity map which is open. But the family f1 f2 does not distinguish this point from closed sets in X. Lemma 3. The statement of lemma 3 is the evaluation function E from X to product of yi is continuous if and only if each fi such that x from yi is continuous. Then the proof of the theorem is, let E from X to product of yi be the lemma third evaluation function. Now continuity of the evaluation function E is continuous follows from lemma third, that it is one to one follows from lemma first, while lemma 2 shows that E is an open map when regarded as a function from X to E of X. This E is one to one continuous and open from X to E of X. Hence, E is an embedding. This is the proof of the theorem, and the application is, if X is a subspace of a space Y, then the including map I from X to Y defined by I of X is equals to X. For every X related to X is an embedding. Thus, including maps are the most immediate example of embeddings. Now, there are some references and external links related to this theorem. Thanks.